I will not talk about the silencing strategies, but there is a group of researchers who think that you can keep HIV silent forever, including Dr. Shenazi in Atlanta. Mario already talked about gene therapy. Basically, this is to create a parallel immune system where the cells are either lacking the co-receptor for HIV or express restriction factors to the virus, thus slowing the replication kinetics. Esper already talked to you about the prevention and the prophylaxis, which is very effective. And I will not really talk about the functional cure. In other words, that you can have long periods where drugs are not required to keep HIV silent. So basically, these are the 4 approaches that are proposed by investigators. The most people work on the shock part, which basically is trying to reactivate the virus from latency. In other words, to activate the transcription of the virus so that the immune system can see it. And there are basically 9 different methods proposed, including PKC agonists, MAP kinase agonists, latency reversing agents like histone deacetylase inhibitors, BET bromodomain inhibitors, 5-azacitidine, toll receptor agonists, growth factors that Rafik talked about, checkpoint blockade, which has been used in cancer chemotherapy, anti-growth suppressors, differentiation agents, anti-IL-10, TGF-beta. Then you have things like UV light, heating the whole body to something like 42 degrees, glycans, galectins, anti-estrogens, combinations of above. Now, because the immune system is not totally active after a long term of HALT, they think that shock should be combined with a kill strategy where you basically boost CTLs, use broadly neutralizing antibodies, again, TLR agonists on both arms because they will improve antigen presentation and also response. T cells with chimeric antigen receptors, CARs, and CMV vaccine. There's also bispecific antibodies that have been used by Margolis and so forth. So basically, this is the predominant strategy by most investigators in terms of being able to wake up and maybe eliminate or at least decrease the viral reservoir significantly. And that's why there's this big arrow here for the combination. As I told you before, there are strategies to silence the virus forever. The most promising is using this dihydrocortistatin A compound, which is a natural product from sponges, sea sponges, and it's an ATP analog, actually, that also blocks CDK8 and CDK19, which are called mediator kinases. Some people suggest that signaling block should work, which is basically JAK-STAT inhibitors. For example, there's a famous drug for rheumatoid arthritis, tofacitinib, cyclosporin A, and also perhaps to induce tolerance by some sort of high-dose effects. Now, the only problem with these treatments is that they're lifelong. They do not really engender a drug-free period of time because you have to keep the virus suppressed forever, and they may also have deleterious effect on the immune system for other infections, including cancer. Finally, there's gene therapy that has been alluded to. So the most hotly pursued is the CCR delta 32, CCR5 delta 32. A number of groups are working on this as gene therapy. Now you can also include or introduce new restriction factors to the virus. You can use TAR decoys to prevent that from working so well. And of course, you can use CRISPR-Cas, that has been alluded to by Mario as well, to either cut the provirus or reactivate the provirus through a delta Cas9 VP64 or a synthetic activator module to activate proviruses in infected cells. So basically, all of these different therapies or different approaches have been proposed by many investigators, and hopefully we'll see in 5 or 10 years whether any of them bear fruit. Now, we also don't know how big the reservoir is and where the reservoir is primarily located. The impression now is that the primary reservoir is not in the periphery, in the circulating lymphocytes, but it's in the lymphoid organs and the CNS. And the reservoir could be rather large, except, as has been alluded to already, about 90 to 95% of all the proviruses are most likely defective. So to really measure the success of any therapy, you would have to basically have access to tissue organs to be able to evaluate your treatment success. Now, how does latency occur in the first place, or how does the virus silence in the first place? Now, the accepted notion is that the virus enters activated lymphocytes, but it actively replicates in those lymphocytes and only gets silenced when the cells go into memory compartment, especially central memory compartment, as alluded to by Rafik. But it turns out that even in activated T cells, up to 5% of all the viruses become silent right at this particular point. And so this is very puzzling as to why the virus should be silenced when the cells are fully activated. And the reason for that is that there's a tremendous amount of transcriptional interference. And I'll tell you just a brief comment on this particular phenotype, because it's hard to grasp, but the virus has already told you how transcriptional interference works. So these are the latency mechanisms: transcription interference, absent transcription factor in resting cells, primarily PTAB and cyclin L-CDK11, which are required for HIV to transcribe and process its RNA. There's a chromatin compaction, and obviously defective viral particles. However, if there are more than one virus in defective virus particle in a cell, infected cell, then you can get recombination and reconstitution of the viral particle. Now, transcription interference has actually not been studied or mentioned very much in the field of latency, primarily because it is hard to detect the RNAs that occur when the virus integrates into an intron of an actively transcribed gene. So what is transcription interference? Well, the virus tells you transcription interference because when the virus is in a completely empty environment and totally open, the 5' LTR starts transcription, but the 3' LTR terminates transcription. In other words, whatever begins here terminates here, and this does not fire. This does not initiate transcription because the RNA polymerase that goes from here to here removes transcription factors from the 3' LTR and allows for cleavage and polyadenylation. So the virus has set it up so that even though it has two identical promoters, only one of them is active. So if that's true, that any polymerase can silence the 3' LTR, then if the virus is in an intron or in a gene which is active, then the 5' LTR is going to look like the 3' LTR, and all transcription will stop here, and then the 3' LTR will look like the 5' LTR, and transcription will begin. And this happens very, very commonly. And when you poison the exosome, which degrades RNA that is either incompletely capped or polyadenylated, then you see both the sense transcripts as well as the antisense. So here the LTR, the virus is integrating the opposite orientation from the host gene. So the host transcription goes this way, and here both LTRs are occluded, or at least are not allowing for transcription to begin from the provirus. And therefore what you have is a host cell gene that has an intron that is longer by this amount. And the only time you see this antisense transcript is when you poison the exosome, which degrades the intronic RNA very rapidly. So by using siRNA against the catalytic site of the RNA exosome, you can now start appreciating the transcription interference which works during activated gene, activated cell HIV integration silencing. And it's a major problem because it's very hard to get your hand on this or to prevent it from happening. So in a paper we published in 2008, it turned out that the gene was PP5A, which is estrogen dependent. The transcription stopped in the 5' LTR, and the moment we basically blocked this particular promoter by using anti-estrogens, in this case tamoxifen, basically the virus came right out. So if you can block the transcription from the upstream or downstream, position, you are allowing for HIV to reactivate and to start transcribing its genome. So that can happen during lifetime of a cell. That can occur because of different external stimuli. This can occur because of estrogen or other hormone manifestations. And the reality is that when you put primary cells in tissue culture, the fetal calf serum has so much estrogen in it that a lot of this transcription interference is even potentiated, and only when you block the estrogen in the serum do you actually now see reactivation of HIV. So this is a very important point that is not really regarded very heavily in the latency literature, but it's a very important consideration for any elimination or cure. So how do you define the latent reservoir and residual replication of HIV? So what has been suggested so far is you just do RNA sequencing approaches or qPCR and immunofluorescence. But we've thought that maybe there's another way, and that was based on studies we studied very early on in 1980s already, and studies we have started in 1990s. And basically what happens is that if you look at HIV infection in the resting state, when there is no TAT and no transcription and no transcription interference, although transcription interference from the 3' LTR can also do the same, you see nothing but short transcripts. So in other words, this is a nuclear run-on where you see that polymerase started on the HIV LTR but has not elongated. But in the presence of TAT or NF-kappa B, you can now see elongation. So basically, in the absence of transcription factors or in the absence of HIV TAT transactivator, you get a tremendous amount of short transcripts. And these short transcripts do not elongate until you activate the virus, until you activate the cell. And they can be detected in cell lines, and they can be detected in patients. So if you take patients and you do PCR with primer 1 and 2, which amplify short transcripts, primer 1 and 3 that amplify long transcripts, you can actually determine that in a latently infected cells, basically you see nothing but TAR transcripts and no long transcript. It is demonstrated here. So in latency, in the periphery where cells are totally unactivated, they're totally resting, every single cell has nothing but short transcripts. This is after seroconversion. So this is just after infection. This is after people have basically been infected for the first time. And the reason that is because circulating lymphocytes are by nature resting. The moment they get activated, they start homing somewhere. So these are truly resting PBMCs and lymphocytes. But in every single case, that we had 10 cases at a time, we could reactivate the virus by here allogeneic feeder cells, and the virus was totally replication competent. Now the immune system, when the immune system involutes and the immune system basically becomes shot by the virus, you can see both short and long transcripts, even in the periphery, because these cells are now activated even as they circulate in the body. So if you can see short transcripts in resting primary T cells, you might be able to see short transcripts also secreted from resting primary T cells. And so that is the basis of looking at TAR in exosomes secreted from cells. Now, the other marker which we have employed is this protein called NEF. And NEF was also alluded to basically before. NEF is a small protein produced by multiply spliced RNAs, and it's most abundant early protein in HIV transcription. And NEF is very good at creating exosomes by itself. So in other words, it's very good at getting excreted from cells. So basically what we decided to do is to use TAR exosomes for true latency and NEF exosomes for residual replication. And so basically there's this diagram here. So the infected cells make virus. The infected cells also make exosomes. And cells can just make no virus, and they can still make exosomes. So the bottom line of the studies, and I don't have all the data because the studies are done in Ljubljana, Slovenia, but most of them for 200 patients now, is that when you look at TAR exosomes, they're very abundant, even in elite controllers. So these are long-term non-progressors versus HIV-negative individuals on heart. And here are NEF exosomes, also in the periphery, of HIV optimally treated individuals. And these exosomes have now been analyzed from 200 people with undetectable viral loads by Jana Ferdin and Metka Lenasi at the University of Ljubljana in Slovenia. And basically what they find is they correlate with reservoirs of latent and residual replicating viruses. So TAR exosomes, true latency, NEF exosome with residual replication, reveal efficacy of treatment and penetration of drugs into sanctuary sites. For example, there are many fewer exosomes in the presence of non-nucleoside RT inhibitors than in the presence of nucleoside inhibitors alone. They also contain microRNAs and surface markers that could reveal their cells and tissues of origin. So in other words, these exosomes not only contain TAR, they not only contain NEF, mostly they don't contain both, but they do contain microRNAs, which by sequencing the microRNAs might be able to predict where they're coming from. In other words, are they coming from the CNS? Are they coming from T cells? Are they coming from monocytes and so forth? So I won't talk much about Timothy Brown because Mario has already told you all about it. It's the only person cured of the disease after 2 bone marrow transplants, only to tell you that basically this bone marrow transplantation with the CCR5 delta 32 bone marrow in Berlin proved to be curative because after 2 bone marrow transplants, he is basically truly HIV negative and also HIV exosome negative, which we find to be important. But so basically right now, the gene therapeutic approaches are trying to recreate the Timothy Brown or the Berlin patient with primarily the CRISPR-Cas9 methodology to basically remove the 32 amino acids from CCR5. But we believe that basically, or we are trying to approach it slightly differently by using TRIM5, ApoBac3G, SAMHD1, and TREX1 restriction factors. Some of them are of a different species so that the virus cannot overcome them. But we think that basically using a natural restriction factor to which the virus has not yet found antagonism because it's from a different species might be as good a gene therapeutic approach. So how do we go after shock and kill strategy? We think that basically you have to attack 3 transcription factors to get the virus going. One is NF-kappa B, the other one is PTAB, and the third one is the cyclin L-CDK11. So NF-kappa B increases initiation elongation rates, also binds DNA so tightly that it counteracts and relieves transcription interference. So NF-kappa B is a very important transcription factor to be activated by any shock and kill strategy or shock strategy. The second one is PTAB, and PTAB is the co-activator of NF-kappa B as well as TAT, and the levels of PTAB are so low in resting cells that in the absence of PTAB, NF-kappa B or TAT cannot work. And so basically, you need to activate levels of this kinase, and you also have to elevate the level of this kinase, which is required for HIV 3' end formation. So, just to diagram, this is the viral genome. The RNA starts at the 5' LTR. It initiates quite nicely to make the short transcripts in the absence of PTAB, but you need to bring PTAB there for the NF-kappa B to work and for TAT to work to elongate transcription. But if you do not have cyclin L-CDK11, then you do not terminate transcription, you do not cleave, and you do not polyadenylate the transcripts, and you have some problem with splicing. So basically, NF-kappa B, PTAB, cyclin L-CDK11. The only way you elevate the levels of translocation of NF-kappa B and PTAB and cyclin L-CDK11 is through agonists of PKC and MAPK kinase, and the latency reversing agents, HDAC inhibitors, bromodomain inhibitors, and so forth, release PTAB from this inactive complex to this active complex. Now, I understand this is very difficult to understand, But the cells, when they make P2B, when they start synthesizing P2B, the vast majority is inactivated because the cell does not want to have much free P2B, because otherwise it proliferates and grows unimpeded. And in fact, a lot of cancers have unrestricted P2B, not in this complex. But for example, Jurkat cells and many of the cells that people study, transformed T cell lines, 95% of all the P2B is in this complex, and only about 5% is active and available for NF-kappa B. So obviously, if you can release P2B from this inactive complex, which happens through the latency reversing agents, then you potentiate the effects of NF-kappa B and TAT for HIV transcription. So the sequence of events for shock has to be that you activate the cells through some sort of activation signal. It could be T cell receptor, it could be PKC MAP kinase agonist, that activates NF-kappa B, increased levels of P2B and cyclin L CDK11. Most of P2B is now sequestered in the inactive complex with RNA. Latency reversing agents, including HDAC, BET, 5-adenosine, chromatin shocks, release P2B from the 7-SK complex. HIV is reactivated. Free P2B increases synthesis of hexim to resemble 7-SK, the inactive complex, but because TAT can steal P2B from 7-SK SNRMP, HIV transcription continues, and that of other genes is turned off. This is a very important Achilles heel of the virus, that even if the hexim reassembles the 7-SK and the cells become quiescent, HIV transcription will continue as long as TAT is made. And these basic principles should inform proper use of these compounds clinically and therapeutically. So just to show you, the levels of P2B are very low in resting cells. The levels of CDK11 are very low, but they can be increased following here PKC activation, or actually CD3, CD28, which I don't have on this slide. So just to reiterate again, the latency reversal agents, for example, SAHA that Mario talked about, vorinostat, need P2B in this complex to work. And that is why they do not work very well in resting cells until you have activated them. Okay, so that's also the principle as to why the synergy there is between PKC agonists, PMA, prostatin, bryostatin, ingenol, and Kansui, and these latency reversing agents, HMBA, SAHA, JQ1, 5-azacitidine, but in this case not farnesyl transferase inhibitors. So Renato Aguiar, who is at Rio de Janeiro, did this experiment together with us using ingenol B, which was synthesized by Luis Pianowski, also in Rio de Janeiro, and was able to show, and in fact, this is the most promising PKC agonist right now to be used, that he got no induction in resting cells by SAHA because there's no P2B. He added ingenol, very nice induction of HIV. This is 24, 48 hours. And if you now combine ingenol B with SAHA, you see some synergy of the two compounds. And usually you can lower the amounts of both drugs and get the same effect. We also did that with ingenol dibenzoate, which is another ingenol compound, which is a bit more potent than ingenol B. And again, you see the JQ1 by itself has no effect because there's no P2B and no cyclin L CDK11. But if you combine ingenol and JQ1, you see a synergistic activation of HIV in resting primary T cells. Now, it turns out that all ingenols are made from a euphorbia plant. Here it's called avalos in Brazil. In China, it's called kansui or gansui. It's a rather pretty plant. Grows everywhere, and this is the root. And the root of this plant has medicinal properties since the Greek times, and probably earlier in Chinese herbal medicine, has been used for water retention, ascites, edema, as well as leukemia and lymphoma. And the only thing you have to do is to grind up this root, and you get 12 different ingenols, 6 cansuinins, and some other eufols, 6 eufols and 4 cansuinins, all bioactive molecules. and they all influence cell growth and proliferation. So the ingenol B and ingenol dibenzoate were both made from the root of this plant, and so we wanted to know if the plant itself would do the same. In other words, if we just ground up the root and gave it to cells, would we get the same effect as the purified ingenol compounds? And that obviously has some resonance because it's very cheap. 1 kilogram of GMP pure gansui root powder can be bought in Shanghai for $15. In fact, the shipment is more than the cost of the powder. Or you can actually go to any Chinese herbal store and just buy the root and grind it up yourself. Now, it turns out that, so this is comparison ingenol B, ingenol dibenzoate, and gansui, that gansui is about 10,000 times less potent than ingenol dibenzoate, about 200 times less potent ingenol B, but the concentration of gansui that gives you a 50% induction of HIV is exactly what humans take, a 50 kilogram human would take for this indication in the Chinese herbal repertoire. So in other words, 1 gram of gansui per day would be enough to activate the virus in infected individuals. And so to compare how gansui works compared to PMA, PHA, or ingenol dibenzoate in terms of patient cells, and these are from SCOPE cohort in San Francisco, you can see that PHA, PMA activates 5 out of 7, that ingenol dibenzoate 4 out of 7, and gansui here 3 out of 7 patients. But this could be dilution effect because these people have been suppressed for viral loads for a very, very long time and have relatively high CD4 lymphocyte count. So basically, they are rather healthy on heart. But then we wanted to look at 5 patients. That's okay. Yeah. So then we looked at 5 patients with a combination of gansui and SAHA, gansui and JQ1, where we could actually lower the dose of gansui by a factor of 10. And now we see that basically gansui and JQ1, this combination of a PKC agonist and an LRA, was able to activate as many patients as PHA, PMA, or ingenol dibenzoate. So in the meantime, there have been reports from Ghana that there is a substance in cacao which is called procyanidin trimer. And this procyanidin trimer was actually as effective in activating HIV as, for example, PKC agonists. So here are some of the data. So this is the procyanidin trimer. This is the dose response of procyanidin trimer. It's a MAP kinase agonist. And you can see here that if you have procyanidin and PMA, they give you a certain amount of activation, but if you combine the two, there's great synergism. So we are actually collaborating with the group from Ghana to use the cocoa, or extract of cocoa, as well as the gansui for a combination reactivation of HIV in the latent cells, plus or minus some LRA or latency reversal agent like HDAC inhibitor or bromodomain inhibitor. But it is possible that that might not be even necessary, because it turns out if your diet is very heavy in meat, you create a lot of butyrate in your gut. And so maybe we could be able to treat people in the underdeveloped country with a combination of PKC and MAP kinase agonists, for example, gansui or avalos and cocoa extract, and then basically either treat them with another latency reversal agent or just allowing them to digest a very meat-heavy diet, which is ideal for Brazil with all this charascurias, and basically would be able to get some reduction in viral load. And this might be able to be done in a very resource-poor countries where you could imagine opening something like cacao box for this particular shock therapy of HIV. So I probably could stop here, because the next part is just about how we have developed assays for every single step of this reactivation. In other words, how we test for new compounds that could be used for shock therapy of HIV. So we have NF-kappa B assays that can be easily applied to primary cells. We have Peter B assays that are now being actually developed for high throughput screening. They have been very useful for cancer therapeutic. There's a paper just came out in Molecular Cell where this assay was used for treatment of melanoma. We have a very nice assay for the reassembly of the inactive complex, so we know exactly the duration of these drugs in cells, primary cells. And we have a very nice assay for CDK11 cyclin L, which is a read-through assay from the HIV 3' and to be able to detect drugs that will affect proper processing of the viral genome. So I probably should stop here and just acknowledge the people who have done the work. So it partly was initiated by Renato, Luciana, and Tatiana Sampaio, who are all Brazilians, with a sliver of people from Eastern Europe and the United States, with collaboration with Paul Lucio, where we've done a lot of monkey studies that I haven't talked about, David Price on Peter B, Amilcar Tanuri in Rio de Janeiro, and I think they have some other promising herbal preparation from the Amazonia region, which work very similar to Gansui or to Ingenol B. So thank you very much for your attention.